Welcome everyone to our talk. Thank you for your interest in what we wanted to share with you on the topic of computer-aided architecture design. My name is Oliver Creighton and I work for BMW. In my part of the presentation, I would like to talk about four main challenges that we see in the design of architectures at BMW. The first challenge is a cultural shift. We want to go away from the signal and function-oriented architectures of the past and move towards service-oriented architectures in the future. So this challenge really means several different things. The first thing is, if you want to have a service-oriented architecture, you need to have that for the entire vehicle, and maybe even beyond that. And so this is a big cultural mindset change that needs to happen. If you think about how we developed vehicle architectures in the past, then you know that much of it is really separated by functions and their signals, the data that they process. And some functions have their own ECUs, and orchestrating reuse is hard to do. There are three consequences of this cultural shift. The first consequence is actually something that we intend to gain. It's a benefit. So an example would be, you have a piece of software that takes sensor data from the different wheels and takes the wheel rotation, and from that derives and calculates the vehicle's center of gravity, speed over ground. This is a more complicated piece of software than one might think, and you do not want to have to do that kind of high-frequency calculation several times in the car. On the other hand, there might be several users of that kind of a service. The exact speed of the vehicle might be used, for example, in the instrument cluster, simply for displaying it to the driver. But it might also be very relevant in the navigation system that is displayed on the central information display, and it might have some kind of way of showing the vehicle speed, maybe in kind of an animation or even just also as the actual speed. Another example might be even simpler, to take sensor data to derive what the outside temperature currently is. And with these kinds of infrastructure provider services, you want to construct a service-oriented architecture for higher level functions of the vehicle. So to have well-defined responsibilities between providers and consumers would enable to reason more systematically and to also validate and test individual parts of the vehicle. The second consequence of this cultural shift from signal-oriented and function-oriented architectures to service-oriented architecture is something we actually need to do. We need to encode more of the system knowledge into the system itself. A prime example of where this is really useful is the actual onboard network. If you define and the system knows what, for example, certain latency requirements are of certain services. Let's take the example of the navigation system again. And you can define the latencies that are acceptable, the deadlines that you have to meet when updating the vehicle speed. You have a better way of designing the architecture in an optimal way. Also, if you encode degradation options, what you can do if certain parts of the system fail, this enables the system to make intelligent decisions on how to gracefully degrade the functionality. So this is something where you need to really make sure that you have an appropriate way to define what the degradation really will look like. And the last example of system design knowledge that you need to have probably in every part of the vehicle is a common understanding of runtime configuration. So, for example, vehicle modes and the startup behavior, the shutdown behavior of parts of the system. Another piece of information might be the kind of redundancy you want to design into the system so that you can meet certain safety goals. And the last bit is on the topic of security, to have a global notion of authentication and authorization. So that's something that also should be unified across the entire vehicle architecture. The third consequence of changing from signal-oriented architectures to service-oriented architectures is something that we need to have new requirements towards the hardware that we employ and the software that we design. Maybe even going into virtualization so that you're able to migrate during runtime functions from one ECU to the other. So that was the first challenge that we see, getting away from signal and function oriented to service oriented. The second challenge that I want to talk about is that of modularity. On the one hand, the security aspects, so to have privacy and trust encoded into your entire architecture. And with that comes the need to really talk about the capabilities of certain services and ECUs and what roles and what rights the customer wants to define for these different parts of the architecture. To really be able to centrally manage that kind of trust and privacy concerns for our customers, we're even thinking about going outside of the boundary of an individual vehicle. So if you think about car sharing use cases, you want to be able to set your personal preferences, your contacts, all kinds of private data, and you want to set that once for all your vehicles that you might be using. And the second example for modularity, which is a challenge, is how to construct a safety case in a modular way so that you can really ensure by design, by construction, that the fault containment regions that you want to use in your safety case are really contained, so that you are certain that if something fails in a certain region in the vehicle, it cannot propagate beyond that. The third challenge, at the moment we conduct a lot of whole system tests. So we have high effort and high costs in integration and in testing. And if you think about that, we're constructing complex systems and we're putting them together, which is a certain amount of effort in itself. And then we're testing the entire system. And so we have a strong focus on automation at the moment because we see that to really enable us to construct ever more complex systems, certain tasks in testing and integration really need to be automated. And with this comes the ability to have some kind of early stage validation and verification, because the more you automate, the more you specify in advance, the easier it is to become also virtual in the kind of validation and verification that we're doing. And with that is a challenge to really come up with test coverage metrics that are really more about the variability and what kind of execution paths have been executed. So you have test coverage metrics more than how many kilometers have been driven with certain integration test cars. The fourth challenge is extensibility. So we see the life cycle of cars has changed and it's going to actually accelerate this shift that we see. If we design an architecture of our vehicles, we have to make very early choices, but not all of them will stick until the end of the life cycle of that particular model. And so we want to be able to add software functions, and we are thinking about strategies how to enable that kind of later updates even in customers' hands. And if need be, we want to be able to replace only very small parts and hopefully cheap parts of the vehicle in customers' hands so that they will be interested in upgrading their vehicles over their lifetime. And so with that, that is the question, how to really future-proof the architecture. So how to make design choices and select technologies that are appropriate for this kind of extensibility of software and hardware. So how could we possibly address these challenges with algorithms? Well, the first challenge, to transition from signal to service orientation, we see there is an opportunity to apply big data and AI ideas and algorithms to correlate what we already have. We have a large set of specifications and designs and interrelated databases that describe how we engineer the vehicles and manufacture them, and to really start mining all of that data and to see what we can learn and how to enable our engineers to make intelligent decisions in the future, more intelligent decisions. That is something where we see an opportunity for algorithms too. And about the verification and testing and integration efforts, we see an opportunity to think about the complexity metrics and to use test coverage calculation and algorithms for that. And the highest challenge, of course, is to be able to simulate the full stack of the entire system with varying degrees of precision. So the idea is to start in the early phases of the development with sort of a rough sketch that is still executable and already executable, and that you can already reason about in terms of critical paths and potential bottlenecks and so forth. So the iterative idea is to start with a rough idea of a certain separation in subsystems, and then become more and more precise and more close to the actual vehicle architecture. And with that kind of a harness, you can plug in software in the loop or hardware in the loop test cases. So in order to really build the trust that is needed in the entire company in the service-oriented architecture. So that's the end of my part. I would like to hand over to Nicolas now, who is going to take you to some of the use cases that we have discussed.
Thank you very much, Oliver. Good afternoon, everyone. So in the rest of this presentation, I'm going to focus on challenge 4, which is the need to conceive architectures that are future-proof. What we'd like to show is that tools, for instance, based on the exploration of the possible futures in architecture, can actually provide some guidance to make better design choices. Answers to a number of design questions have already been provided in prior works. For instance, we studied what's the total capacity of a candidate architecture in terms of the number of streams or services it can support. Can we improve the architecture by removing bottlenecks? Can we make an architecture less expensive without sacrificing its capacity? In the following, we'd like first to present proposals to take costs into consideration when making design choices, and second, we'd also like to illustrate how algorithm can help design an EE architecture by deciding where to add processor and network devices. Well, the algorithmic tools mentioned before fall under the umbrella of what can be called EE architecture design automation. And this can become today a reality because the technologies we need are mostly available. First, we need to work on models on virtual platform. Then once model, we need to be able to automate the configuration of the system's parameter. We then need to evaluate the achievable performance by simulation and worst-case analysis. We need high-level function to improve candidate solutions in different dimensions: cost, capacity, reliability. We may even have the architecture partially generated as discussed later. In that landscape, we anticipate the role of AI to be increasingly important. First, to speed up computations, for instance, replacing simulation by prediction, and also to speed up the development of configuration algorithms by reducing the need for domain-specific expertise. Now, let's present BMW's prototype architecture that will serve as an illustration next. Well, this architecture is representative of the design choices of OEMs today, and also representative of the challenges they are facing with functions requiring both computing power, security, and safety. So at the core of it, there is a powerful central computer, the application platform, which runs functions pertaining to the dynamics of the vehicle, to the infotainment, and which runs some ADAS too. As we can see, there are 3 zone controllers, each hosting dedicated functions and serving as gateways to the CAN and to the LIN buses. What we see here is a model of the architecture in the PGS software from Iterative. Overall, we have 17 ECUs, including powertrain, HMI, charging. The links are 100 megabit per second, except the links between the switches, which are 1 gigabit per second links. We assume a standard automotive traffic comprising 30% of command and control streams, 5% of audio, 5% of video, including some ADAS video streams. And the rest of the traffic is created by a number of TFTP infotainment streams and by various services, making up about 60% of the overall traffic. Now, this slide is provided for reference to give you more details on the analysis mentioned, and in the following, we are going to focus on the cost extensibility analysis, the red block at the center, and also on the synthesis of architecture, which is the purple block. Now, let's consider the architecture presented before. Well, we'd like to estimate how many more services this architecture can support in addition to the baseline traffic. That's what we call the total network capacity, and it's defined as the number of additional streams or services that an architecture will successfully schedule with a given probability. This probability is called the assurance level, and we are going to use 75%. Now, of course, the capacity depends on the TSN scheduling solution. So here we consider 6 solutions, including CBS HP, that's 2 credit-based shaper classes, that's a top priority level. Preemption plus CBS, it's a top priority express class with 2 CBS classes below. Then TAS plus CBS, a top time-aware shaper class at top priority, followed by 2 CBS classes. Now, the total network capacity is computed by Monte Carlo simulation. In the figure, the x-axis is the number of additional services, and the y-axis the probability to successfully scale that number of services. Logically, the more services are added, the less likely it is that the network can keep up with the load, hence the downward trends of the curves. Well, in our specific application, the 2 most effective solutions are the one with both a top priority class dedicated to control flows and shaping for the audio-video streams immediately below. Using the best solution, which is an express class plus 2 CBS classes, the architecture will be able to meet the communication requirements of 55 additional services with a probability of 75%. Now, up to now, we have considered only the raw performances of the TSN scheduling solutions. but there is a cost associated to each solution. And the cost can actually be any quantity. Of course, there is a monetary cost, but it could be also the development time, the risks, the weight. And that's because different solutions, different architectures will require a different set of hardware components. The cost model proposed here is built on the idea that in addition to a base cost, the price of a switch is proportional to the number of ports it has. And the price of a single port depends on the capabilities of the switch. Does it support CBS, QCIs, the time-aware shaper, and so on and so forth, and at which data rate? And it's up to the user to instantiate the model with data from suppliers or with the estimates. It should be noted that to reduce the costs, it's possible to apply TSN mechanisms like shaping, preemption, or replication only on specific network devices at well-chosen locations. And that's, in our view, a promising avenue to optimize cost. Now that we know the extensibility they allow and their cost, we can compare the different TSN options in terms of the cost evolutivity trade-offs they offer. In the figure on the x-axis, we have the number of additional services the TSN solution allows, and the y-axis shows the cost of it. Some solutions will be better than others. For instance, we can see here that concise priorities, that's the use of the 8 priority levels without anything else, is less expensive than other options for the same extensibility. But some options are simply not comparable. For instance, CBS plus preemption is much better than the others in terms of extensibility, but it's also much more expensive. So what can be done here is a Pareto analysis to identify the options that offer the best distinct trade-offs. And with this data, it can be decided whether it's worth investing in expensive TSN mechanisms with respect to the amount of new functions and the additional platform's lifetime that they allow. Now, at this point, we are going to go beyond the concept of network capacity to evaluate what we call the total architectural capacity by considering the CPU load induced by the additional services. And we'll focus on the best performing TSN solution, which is an express class at top priority and 2 CVS classes below. Now, the blue curve in the figure is the probability to support a given number of additional services without considering CPU requirements, while the red curve is when taking into account CPU load requirements in addition to communication requirements. Here, at the assurance level we are interested in, 75%, the constraints on the CPU load reduces the capacity by only a handful of services. But that's because the services are mostly I/O bound. But in other contexts, the CPU power will be the limiting factor, and that's something that can be learned from such analysis. Now let's move on to the last topic of this talk, which is the extension of the core topology. We assume the designers know the kind of topologies they want, typically a zone-based architecture with a powerful central computer. The traffic within the core topology is partially known too, because there is already some visibility on the functions executed on the processor. Now the design question is which hardware components to add and where in the architecture in order to obtain an architecture that is the most efficient with respect to an evolution scenario. Typically, the evolution scenario would be adding new software before the release of the vehicle and later when in the hands of the owners. Or it could be adding new ECUs, typically ADAS or infotainment systems at a mid-generational refresh. Of course, there are many goals and practical constraints to be considered in the design space exploration, like topological constraints, proximity to sensor, reducing the overall cabling length, and so on and so forth. There are also security and reliability constraints, like the need to segregate flows of different criticality levels, or the need to have multiple paths between ECUs if that's needed with respect to reliability objectives. Now, what kind of hardware components can be added to the core topology and for which benefits? Well, we can of course add computing power with ECUs, processors, SOC. We can add switches. We can add ECUs with an internal switch. We can add links between switches to increase the bandwidth. We can add a network interface to ECUs to get dual-home ECUs and implement load balancing or frame replication. Now, the question the algorithm can answer is what to add and where in the topology. We are now going to illustrate the synthesis approach with a few topologies created by an algorithm that adds ECU to a core topology. And the algorithm does that considering a parameter that defines a trade-off between balancing the topology in terms of the number of ports used on each switch and placing additional ECUs close to, that is on the same switch as the hotspots, which are the ECUs that we know are likely to support many more services in the future. And thus the added ECUs will allow to offload the hotspots with minimum additional traffic and minimum latency. The hotspot here is the central computer. We illustrate with three computer-generated architectures. The most balanced architecture is on the left-hand side, and the least balanced is on the right-hand side. Now, which one will be the best can be evaluated with the criteria and the techniques presented before. And the results will depend very much on the evolution scenarios that has been foreseen. Now, of course, daisy chain and bus topologies, as well as CPUs with different computing powers, open up many more possibilities that can be explored by the design space exploration algorithm. Now, let's get to a few concluding remarks. We think that the technologies available today could enable us to automate much further the design of TSN-based architectures, and that would probably yield benefits in terms of costs, time, and evolutivity. Now, in the short term, the question is whether and how such kinds of techniques can be introduced into the existing design process and design flows of OEMs. And that should be done anyway with a clear understanding of the expected benefits and limitations. In the longer term, it's very possible that design automation techniques at large are going to play a major role in the evolution of the innovation process and the organization of R&D, but that's of course too early to tell. Thank you very much for your attention, and we will of course welcome any questions you may have.